Have you ever looked at a tiny little data sample and wondered, how can this possibly tell me anything about the big picture? Well, today we're diving into an awesome statistical trick where data, believe it or not, pulls itself up by its own bootstraps to tell us what we need to know. Right? So this is the core challenge, isn't it? You've got this small sample. Maybe you polled just 100 people or you ran a tiny experiment. But what you really want to know about is the whole population, the entire country, everyone. So how do you handle that massive uncertainty when you've only seen a tiny slice of a giant pie? All right, so how do we even begin to tackle this? Let's start by looking at the traditional way, the old school approach statisticians have been using for decades. Typically, you'd start with what's called a point estimate. It's just a single number. So say you want to find the average height in a country. You grab a small group of people, measure them, and find their average height is, let's say, 5'9". That's your point estimate. It's your single best guess, but let's be real, it's almost certainly not the exact average for the whole country, right? It's just an estimate. And that's exactly why a single number just doesn't cut it. It gives us zero sense of how certain or uncertain we are. What we really need is a range of plausible values. You know, an interval estimate, which you've probably heard of as a confidence interval. So instead of just saying the average height is 5'9", it's way more useful to say something like, we're pretty confident the true average is somewhere between 5'8" and 5'10". See? That range is everything. It captures our uncertainty. Okay, so how do we actually build that range? For years, the go-to has been the textbook method. But, and this is a big but, it comes with some pretty surprising limitations, especially when you're dealing with messy real-world data. So the classic method relies on a very rigid, very specific mathematical formula, kind of like the one you see here. Now, don't worry, you don't need to be a math genius to get the main point. The key takeaway is simply that this whole approach is built on a bunch of really strict rules about how our data is supposed to behave. And here's the biggest rule of them all. That classic formula, it really only works if your data fits a perfect, beautiful, symmetrical bell curve, what statisticians call a normal distribution. Basically, it assumes your data is super neat and tidy and predictable. Yeah, think of this old school method as having some super strict entry requirements. For one, it often assumes we know things that are basically impossible to know, like the true variance of the entire population, and it demands that our data be perfectly normal. But you know how it is. Real-world data is almost never perfect. It's messy, it's skewed, and what if you want a confidence interval for something other than the mean, like the median? The textbook method just kind of struggles. And this is where our hero finally enters the story, the bootstrap method. Back in 1979, this totally revolutionary idea came along that used the power of modern computers to just shatter all those old statistical chains. Seriously, before 1979, dealing with messy, non-normal data was a statistician's nightmare. Then this guy, Bradley Efron, introduces the bootstrap. It was a brilliant idea, but it required a ton of calculations, something that was only really possible with the rise of computers. And it changed the entire game. And this is where it gets its amazing name. The whole idea is to use the data sample you already have to figure out its own variation. You don't have to assume it fits some perfect theoretical curve. No, the data itself tells you its story. It tells you how much it might have jumped around if you'd taken a different sample. It is quite literally pulling itself up by its own bootstraps. So here's the bootstrap principle in a nutshell. You take that one sample you have and you pretend it's a mini universe. It's your best stand-in for the real whole population. Then, using a computer, you draw thousands and thousands of new samples from this little mini universe. And for each new sample, you calculate your statistic, the mean, the median, whatever. You just watch to see how much that number jumps around. And that variation you see, that gives you a direct, real-world estimate of your uncertainty. It's genius. So, okay, it sounds like magic. But how does it actually work? Let's pop the hood and take a look at the engine here. This clever process called resampling. The heart of the bootstrap is something called sampling with replacement. So think about it like this. If you're dealing a hand of cards, once a card is out of the deck, it's gone, right? You can't deal it again. That's without replacement. But now think about rolling a die. You can roll a 6, and then you can immediately roll another 6. The 6 is always there as a possibility. That's with replacement, and it is absolutely the key to this whole thing. All right, here's the recipe, step by step. You start with your original data sample. Let's say it has n items. Step 2, you create a brand new bootstrap sample of the exact same size, n, by randomly picking from your original data, but, and here's the trick, with replacement. This means some of your original data points might get picked 2, 3, 4 times, and some might not get picked at all. For that new sample, you calculate your statistic, like the mean. Then, you do it again, and again, and again. You repeat this thousands of times. At the end, you've got this huge pile of thousands of means, and just by looking at how spread out they are, you get a beautiful, direct picture of your uncertainty. And when I say thousands, I mean it. We're often talking 10,000 times or even more. This is exactly why the bootstrap really took off with modern computers. You're basically letting the machine do all the heavy lifting, creating thousands of these little what-if scenarios from your data to map out the landscape of uncertainty. Okay, so we've built our interval. Awesome. But now we have to talk about what it means. And this is crucial, because how we interpret this is probably one of the most misunderstood concepts in all of statistics. So let's get this crystal clear. Here's the mistake pretty much everyone makes. You create a 95% confidence interval and you say, okay, there's a 95% probability that the true population mean is inside the specific interval. It sounds so right, doesn't it? But it's wrong. The correct way to think about it is this. The 95% refers to the method. It means if we were to run our whole data gathering and interval building process 100 times, we'd expect that 95 of the intervals we created would successfully capture the true population mean. So the big takeaway is this: your confidence is in the method, not in any one specific interval you happen to calculate. Once you've got an interval, it either contains the true value or it doesn't. We don't know which. Our confidence comes from knowing we used a process that works 95% of the time. So that naturally leads to a really interesting question. Is this whole long-run success rate thing the only way to think about it? I mean, what if you do want to say something like, what's the probability the answer is in this range? Well, it turns out there's a whole other world of statistical inference called Bayesian statistics. It's a different philosophy. The approach we've been talking about, the frequentist one, sees the true population parameter as one single, fixed, unknown number. But the Bayesian approach flips that. It treats that parameter as something that can have a probability distribution. And because of that, it lets you create something called a credible interval, where you can actually say, given my data, I believe there's a 95% probability the true value is in this range. It's the answer most people intuitively want. And this just highlights a really deep and fascinating idea in statistics. A confidence interval and a credible interval might end up looking very similar on paper, but they are born from totally different philosophies, and they answer fundamentally different questions. It really shows you that how we frame the question about uncertainty completely changes the nature of the answer we're allowed to give.